Here we want to find the particular solution with this initial condition for this matrix equation. Okay, so we know that we have to solve the eigenvalue problem. So let's find the eigenvalue of that transformation matrix here. And the vertical lines indicate that we want the determinant of that. We can factor out a negative and we get lambda minus 2 times lambda minus 6, factored out another negative, minus 4 times negative 1. All of that has to be equal to 0. Now these two negatives go away, and here we'll have lambda squared. Now the sum of the two numbers is going to be negative 8 lambda, and their product is going to be positive 12. And then we're going to have negative 4 minus 1, which is positive 4. All of that is equal to 0. Well, that's going to be lambda squared minus 8 lambda plus 16 equals 0. Can you think of two numbers that multiplied together are equal to 16 and positive 16 and added together are equal to negative 8? I think I can think of negative 4 and negative 4, which means that lambda 1 is equal to lambda 2, which is equal to 4, which means we have multiplicity. Now remember, there can happen two things. Either we're able to find two independent vectors, or we have to use the theorem for multiplicity in this case. So first of all, let's plug that lambda back in. So 2 minus lambda, which is 4. 2 minus 4 is negative 2. 4 stays the same. Negative 1 stays the same. 6 minus 4 for the second row, second column. 6 minus 4, that's equal to 2. And then from here, we're going to have our x, which is, we'll call it x and y. X, y. And we know that that has to be equal to the 0 vector. Now if we do this, we notice that these two, we can just use one equation because the two are dependent, linearly dependent. And we see that 4y is equal to 2x, or that y is equal to 1/2 x. So for x equals to 2, y is equal to 1. So we can say that this is one of the vectors. Okay, now what is the problem? Can we find another vector with this that is not linearly dependent? No, because there's no way to introduce a 0 only in one of the two entries. So we'll have to use the idea that we can find a second solution with the form that looks like this. The form is t times k times e to the lambda 1 times t plus, no, now we don't have k, now we have p e to the lambda 1 times t. Now how do we find that? Well, it turns out that we can find p if we basically take this equation, and now instead of 0, 0, we put so this is our P1 and P2 values, and we put 2 and 1, which is our k vector. And then we try to solve this. So we're going to have negative 2p plus 4p squared is equal to 2, and negative p1 plus 2p2 is equal to 1. So we can say that 2p2 is equal to 1 plus p1, or that p2 is equal to 1 plus p1 over 2. And we can plug that into the above equation, so we get 2p1 plus 4 times 1p1 over 2 equals 2. Now this cancels. This becomes a 2. We got negative 2p1 plus 2 plus 2p1 equals 2. And what we get is what we should get, which is a statement that's always true because these two are linearly dependent. So a good way to actually find the answer would be to put this in reduced row echelon form. And if you do that, you're going to get 1, -2, 0, 0, and -1, 0. So you're gonna, you can say that P1 minus 2P2 is equal to -1. So let's say that for P2 equal to 1, then we're gonna have P1 is equal to P1 minus 2 times 1 is equal to -1. So P1 is equal to 1 as well. So we get that the P vector now is 1, 1. And now from the theorem above, we can say that a second solution is this solution right here. It's going to have T times K, which we found to be 2, 1, times e to the 4t plus 1, 1 times e to the 4t. Now be careful, this is not a general solution. This is one solution. The other solution is this one right here, the first eigenvector that we found. So the general solution now becomes C1 times 2, 1 e to the 4t plus C2 all multiplied by t times 2, 1 e to the 4t plus 1, 1 e to the 4t. And I can close this parenthesis. And this would become the general solution of our system. I hope you understand the process here. And, well, actually, I'm not done yet because now we want the particular solution with x of 0. So this is a function of time, as you can see. So now, if you want to find the actual particular solution, we're going to have to say that this is equal to, well, what do they tell us? -1 and 6. And that's equal to, let's see, C1 times 2, e to the 4 times 0, that's just 1, plus C, this term just goes to 0 because it's multiplied by t. And then we have C2 times 1 times e to the 0. And then at the bottom we have C1 multiplied by 1 plus C2 multiplied by 1 again. And then, how do we solve this? Well, now we have two equations, two unknowns. We can say -1 is equal to C1 times 2 plus C2. And 6 is equal to C1 plus C2. So, I can say that C1 is equal to 6 minus C2, which means that C1, that -1, is equal to 6 minus C2 times 2 plus C2, which is equal to 12 minus 2C2 plus C2, which is equal to 12 minus C2, or C2 is equal to 13. Now, if C2 is equal to 13, then C1 is equal to 6 minus 13, which is equal to negative 7. Okay.